Welcome to our Saito's group at GScience. We are the group that focuses on green chemistry and circular economy. Especially we'll focus on sustainable polymeric materials for circular economy. So just wanted to introduce myself. I graduated in Japan and I got my PhD as a polymer chemist, which is a chemist focused on making plastic resins, coatings and so on. After that, I moved to the United States and studied green chemistry. And green chemistry is a study focused on doing chemistry in environmental friendly way. After that, I moved to Australia and started my career at Monash University, Australia. And I spent 13 years there. And I moved to Kyoto University in 2020 in October. And I started this green and polymer chemistry group, but focus on circular economy. So we are focused on circular economy, and the circular economy is the field that we wanted to reuse and recycle all the chemicals and materials that we produce. In the circular economy world, we should focus on plastic waste issue. We have to find a solution to solve the ocean plastic waste or the plastic pollution waste issue. So our group is focused on creating a new solution for that plastic waste, such as creating dynamic polymers, which are easily reused and recycled. Dynamic polymers are the polymers that as I mentioned, easily reuse and recycle. To do so, we are connecting the starting material using reversible reactions. For example, we are using reversible reactions such as Velcro type reaction in English, or in Japanese we call as a magic tape reactions. So we are connecting the starting materials using those reactions so that we can connect and release, so that we can create the polymers, but also we can bring it back to starting materials easily. Especially our group is focused on photochemical reversible reaction, which means that we are using photochemical reaction, which is photo, the light source, to create the plastics and bring it back to starting materials. So create the polymeric materials and bring it back to starting materials, only using light. So I'm not going to talk about the detail, but especially we are focused on thymine-thymine dimerization, which are the reactions that we can find in our DNA. So that in our DNA, there's thymines, one of the DNA bases. Those thymine can form the bonds and break a bond by UV radiation. And that's one of the mechanisms of the skin cancer. We are using that kind of mechanism to create a plastic using light source. Try to make the plastic by light using thymine-thymine dimerization, and we can bring it back to starting material by breaking those dimers, thymine dimers. And we can reuse and recycle those things. Also, we are focused on creating self-healing materials, which are the materials that we can reduce the waste itself. So we wanted to increase the lifetime of the material, so we don't have to make any waste. To do so, we are making the materials that we can heal the crack or scratches on the surface. So how we do it? We turn the hard material to soft and soft material back to hard again. So when there's a crack on the hard surface, the crack just stays there. But when we can turn those hard material to soft material can heal the crack. So after we heal the crack as a soft material, we bring it back to hard material so we can use again. So we are doing that kind of thing using reversible reaction as we just explained. So this is the chemistry that we just explained. So you can see that this case we're using coumarins, not thymines. Coumarins can do the similar thing. We can form the bond by light and we can break the bond by light. And we're using that coumarin chemistry to make this self-healing polymers. As we can see here, the big crack can disappear after UV radiation. And this is the data that's showing that the crack disappears. And also the hard material goes to soft material. And soft material goes back to hard material. We are using similar chemistry for gas separation as well. So same chemistry is applied. So we form the bonds and break the bond. By using that reversible reaction, we create the membrane that only specific gas can pass through. So this is showing the membrane that only carbon dioxide can pass through or carbon dioxide can't pass through. And we make that kind of specific membrane. So we are using similar chemistry to create reversible adhesive. So this adhesive can stick to substrate together by UV light, but we can detach it by UV light. So if you want to stick to substrate, we can by UV radiation. But if you want to detach it, we can irradiate different UV light and we can detach it, which means we can keep using same adhesive, attach and detach multiple times. So we're also using this renewable resource to make the same kind of materials, self-healing materials or reuse of adhesive. In this case, we're using soybean oil. And also we're trying to use lignin, which is one of the wood tissue, to create self-healing materials and adhesive as well. Lignin is one of the wood tissue which we can get as a lot of waste from paper pulp industry. But the lignin itself has a complicated chemical structure. So first we have to find the solution to break lignin down so that we can use to create self-healing materials or reusable adhesive. So for example, this case we're using a simple visible light irradiation to oxidize the lignin so we can easily break down the lignin into small molecules. This research is showing that we can break down the lignin using specific green solvents such as ionic liquids. So by using this green ionic liquids, we can break lignin down to small molecules as well. So after we break the lignin to small molecules, again we can create a new materials such as self-healing materials or reusable adhesive from lignin. Yeah, so this data is showing that even from lignin, we can make the reversible adhesive, which is the material we can attach and detach it multiple times. So I just rapidly explain what kind of research that we are currently doing at the group, but we're not just doing that chemistry research as well. We are the G-size group. We do have a lot of different students focus on a lot of different fields as well. So you can see this is my group photo. And there are some researchers that focus on chemistry, but there are other researchers that focus on non-chemistry research as well. So you can check what kind of research we're doing on our website. So as I just explained, our G-size, our graduate school, is focused on transdisciplinary research. So there are a lot of researchers that focus on a lot of different fields. Even my group, as I said, there's a students focused on chemistry, but there are students focused on non-chemistry research. And all those students are discussing every day and try to create a new type of research, transdisciplinary research. So if you join my group, of course, you can learn chemistry, green chemistry, and circular economy, but you can also learn other stuff as well. And also just wanted to explain that we are a 5-year PhD program. So you can join our graduate school just after bachelor, but also with master, but you have to spend 5 years to receive PhD. And we do have a lot of different type of specific programs that you might be interested in, so please check our website. So if you're interested in our group, or if you're interested in G-size, please feel free to contact me. So this is my email, and also we do have a website explaining what kind of research we're doing as well.
Hello, my name is Muhammad Hafiz Ashafa. I'm a graduate student of Kyoto IUP, and now I'm currently studying in this lab, the Green Chemistry and Circular Economy Lab. In this lab, I get to learn not only chemistry, but also many other things involving what is to be the future, green chemistry and circular economy. In this lab, I also get to do many fun events such as fireworks and then camp, but also get to meet a lot of good and important people. Please come to this lab.